actually is produced by delta J equals -1. You basically therefore have this spectra that is spanning on both sides. If the 0, 0 could have occurred, it could have occurred somewhere in between. It doesn't occur, well, I know selection rule prohibits a delta J equal to 0 transition in most molecules. You know what that means. There will be molecules where you will see it. Now we will not worry about it. Not seeing delta J plus 1, delta J minus 1. We therefore call this as two branches of the vibration rotational spectrum. There are two branches, and this branch is called the R branch, and this branch is called the P branch. The P branch has a delta J equals -1 selection. The R branch has got delta J plus 1 selection. And you can see why this should be at a higher energy than this other by just looking at the diagram. 1 to 2, what line is it? R line or P line? It goes 1 to 2. R, because delta J is plus 1. This must be the R line. And what is 1 to 0 will be? It's a P line because delta J equals -1. Which is greater energy. R is greater energy than the P, and that's the reason why all the R lines will show up on this side and all the P lines will show up on the lower energy side. So you have a P line and you have the R line. R line is a manifestation of delta J equals plus 1 selection rule. The P branch is a manifestation of delta J equals -1 selection rule. There is no delta J equal to 0, at least to begin with. But if the molecule, there are some molecules that will show you delta J equal to 0. If it could show delta J equal to 0 selection rule, what would you want to call that branch as? It has to come somewhere over here. That's why they kept the place vacant. So you have a P branch, you have an R branch. Sometime 2 weeks later or 3 weeks later, we will start studying Raman Spectroscopy. And in Raman Spectroscopy, you will find that the selection will be very different. Plus minus 2. If it is plus minus 2, where do you think those lines must appear? Further out. And what would you want to call that? S branch. And what would you want to call that fellow as? So now you start up. That's one of the reasons why you know your ABC quite well. You can name all. If you have O, P, Q, R, S, these are the branches. Don't worry about old S now. The time will come when you have to worry about it. Don't worry about the Q for the entire course. When you do molecular spectroscopy at the 4th level, we will teach you all that. As far as we are concerned, we will look at P and R. R being delta J equals plus 1 and P being delta J equals -1. We'll stop here and we will get back to this. We will write down the equations. We will see whether we can come up with a general formula to illustrate these transitions. And what then happens is we will throw in centrifugal distortion into this problem. That's the next complication. And after having sorted that out and you all feel a huge sigh of relief, they'll come back and tell you, well, the vibration and rotation are really not uncoupled, they are coupled. And when they get coupled, you know what the problem is going to be. The problem is going to be that the value of R, which we assume to be the same, is not going to be the same. So then that's another complication. And by the time you're done with all of these, you will have learned enough of vibration rotation spectroscopy. What I'm also trying to do is for you to record the vibration rotation spectrum of HCl in your 211 lab. And when you record the vibration rotation spectrum of HCl, you will essentially see all the things that you're learning today. You will essentially be able to do that. And the problem we will then, the question that we will throw at you is record the HCl's vibration rotation spectrum and hence calculate the bond distance for HCl. So you will essentially be doing a calculation or estimation of a bond length of a molecule using infrared spectroscopy. So all this while you will be looking at characterization. We will do some physical chemistry experiments. We are trying to prepare some HCl gas phase for you, put it in the cell and give it to you. You don't have to make the HCl. Corrosive, and the last thing we want is an accident in the lab involving HCl. So we will give you a cell filled with HCl. You will record it, By the time you have done the experiment, you would have gone through the analysis of how the experiment has to be done, and you will see some interesting changes over there. What's the nice thing about chlorine? Isotopes. You got a 35 and 37. And what's the ratio of 35 to 37? 1:3. 37 is lower contained. So we have 3 more. So if you take natural chlorine, take natural chlorine containing compounds, you will find that there is a 1:3 spread of the 35 and 37. And you know what happens when the mass changes? The rotational constant changes. What else changes? The frequency, vibration frequency changes. Therefore, when you record the spectrum, you will see all these spectra corresponding to both the HCl35 and the HCl37. So it will be a nice experiment. And hopefully in about 2 weeks' time, you will have that set up neat. So after you run through your present set of experiments, you will do that. By which time you will have also gone through the analysis. So you should be in a position to basically analyze it. Okay, let's stop here. And